Okay, so we're going to look at an example problem with free fall and how, even though something is not given as a value in our equation, or excuse me, in our story problem, if we know we're in a state of free fall, we have some information that we can assume that's not actually given, or infer is a better way to say that. So I'm going to do a couple examples out of your book, looking at the model that we're using in class to try to get you practice with how to examine that full model, and then looking at that free fall idea. So example number 2.13. A rock is released from rest at the top of a 100-meter tall building. How long does the rock take to fall to the ground? And what is its impact velocity? How fast is it going when it hits the ground? Okay, so to conceptualize the problem, we need to know what object we're interested in examining. And in this case, that's the rock. We then have to conceptualize the initial and final. What begins the motion, what ends the motion. So it begins the motion when the rock is dropped. And this is important as I've always talked about how important it is to really comprehend and to really be explicit about what begins the motion and what ends the motion. Because this gives us information, and some of that information isn't provided, but because we've defined the motion and we're able to define the motion, we have the information. It's implied. It ends when the rock hits the ground. Again, this is another thing to be thinking about. As soon as the rock touches that ground, we don't care anymore. It's moving when it touches the ground. So it's still going to be moving at the end of our motion, even though it might blop dead and not move after that, or somebody might catch it, or it might make a hole in the ground. I don't care about any of that. As soon as it hits the location at where the ground is at, as soon as it hits the ground, we are done caring. We want to think about what type of problem this is. So we're working in a single dimension. We're still in 1D motion. It's a single object. It's falling through the air, so it's not changing its acceleration as it does so. And because it's solely under the influence of gravity, it is in free fall. So these are some of the questions you ask yourself. Whether you write them down or not is up to you. I'll be able to assess whether they're part of your problem. But they're good ways to start wrapping your head around how you're going to tackle this problem. All right, so we've conceptualized the idea. Let's set our world up, and then let's tackle the problem. So here's our building. Let's say that we set the origin at the top of the building where the rock is released. So there's my origin moving in this direction. I'm going to call that negative. I tend to like to stick with convention. All right, so what is our knowns, unknowns, and now implied? We have an initial and final position, initial and final velocity, acceleration, and time. And writing this list every time allows me to know that what you are able to pull from the problem. We've set our origin at the location of the rock when it's dropped. So it starts at 0 meters. It says that the building is 100 meters tall. So this position then becomes negative 100 meters. It's below the origin. It's going to have a negative value. It drops the initial velocity. That's not given in the problem, but we're told that the rock is dropped. And that means that it starts at 0. Right when I let go of it, there is no motion. Right when I let go of it, the rock is starting to move. It starts at 0 and it immediately begins to accelerate. Final velocity, we don't know. Let's assess what we might think it is. If it is moving, it's going to be moving when I let go of it, so it's non-zero. It's moving in the downward direction. So we're going to imagine that this is going to end up with a negative non-zero value. Okay. The acceleration. Well, I've dropped it. I'm no longer influencing it. We're assuming no air resistance until otherwise stated. It's in free fall. And anytime an object is in free fall, whether I drop it, whether I throw it down, whether I throw it up, we have a negative 9.8 meters per second acceleration in that dimension of free fall. And the time is not given in the problem. So there's our list. It's asking us how much time does it take for the rock to fall? Well, that is a time interest. So we want to know what the time is. Time is in two relationships. So we think about which is going to be the better of the two. Well, I know more with my final position relationship. So just writing that relationship down helps us remember it and get it in our minds and what's important, not make mistakes. X final is negative 100. X initial is 0. V initial is 0. Time we don't know. Plus 1/2 negative 9.8 time squared. So I have one equation, I have one unknown, I can solve it. So my time for the fall is equal to 4.52 seconds. All right. What about the second half of the question, which asks, how fast is it going when it hits the ground? So that's really our final velocity. What is that velocity as soon as it hits the ground when I quit carrying? And we know that V final is equal to V initial plus acceleration times time. V final is what we're interested in. So that's its variable. V initial is 0. Acceleration is negative 9.8. And my time is 4.52. So I can calculate V final to be negative 44.3 meters per second. And it is what we expected. That negative value tells us it's moving down. Good. So how do we solve a problem with free fall? Well, we get to make some inferences. There are some things that are implied. In this example, if I'm in free fall, regardless of how that free fall looks, my acceleration is negative 9.8. It is always negative and has a value of that 9.8. In this other information that was implied, this rock was dropped. A dropped object has a velocity initial equal to 0. So that was also not given, but we could get it from the information as we recognize what free fall and various ways an object is in free fall is involved. All right, good job.